Hello everybody, and welcome to topic number 4, linear inequalities. Here are our objectives for today's notes. We're going to show you how to solve linear inequalities using different types of properties. As well, we're going to show you how to be able to successfully write answers in interval notation. To begin, let's introduce you to our 4 inequality systems and what they mean. Here I have them written down. The first two are less than symbols. The first one here where I have it is saying x is less than 3. Meaning I need to pick a number that's less than 3, not including 3, because 3 is not less than 3. Here for the second one, I have x is less than or equal to 5. Here I can include the 5 because it's less than or equal. I know I've got the equal sign underneath, so that's what tells me it is less than or equal to. If the arrow points to the right, it's greater than. So here, this is x is greater than 4. That means I could pick any number that's bigger than 4, but I cannot pick 4 itself. The last one is x is greater than or equal to 6. Here, 6 is a solution because it's greater than or equal to. Again, you'll notice the line underneath the inequality. That represents that we are doing equals. Ways to write our solutions. Here we're going to typically write our solutions in interval notation, but let's set you up with a couple other ways that we can read it. On the left side of the column, you'll see set notation. And basically the way set notation works is it's saying x is a number such that, and then the inequality. So for the first one here, x is a number such that x is less than some value of a. Then we have the graphs. You'll notice the graphs have parentheses or brackets. We'll get to what those mean in a second when we get to interval notation. Some of the graphs go forever in one way or the other. Those are called unbounded graphs. Whereas some of the graphs, like we have here on the right side, are bounded between two numbers. Then we have interval notation. Interval notation is the most common way we're going to represent our answer here. A couple things we'll know about interval notation. We either have parentheses or brackets, or a mix of both as we go through and do interval notation. The parentheses we use for anything that's less than or greater than. Basically, if it's not equal to something, we use a parenthesis to represent it. Whereas the bracket, we'll use it if it has an equal sign underneath the inequality. So we'll use it for all less thans or equal tos. You'll also notice that some of them have infinities and some of them do not. If they're unbounded and they go one way forever, they're going to have infinities. We have both negative infinity and positive infinity. We'll use negative infinity anytime we have a less than symbol, whether it's less than or equal to. Negative infinity just simply means that it is going to the left forever because it is getting smaller. Positive infinity we'll use for anything greater than or equal to. It just means it's going to the right forever when we graph. As you'll notice as you look at the infinities, infinities always have parentheses. Never will we go through and bound them. So anytime we use an infinity, it'll always have a parenthesis that's written around it. You'll notice over here on the right, these are bounded. They have two numbers. We're graphing in between those values. So here it's saying x is a value such that x is between a and b, whether it includes a and b or not. The last one tells us x is a value such that x is a real number. In this case, we see everything's graphed, and we have infinities going both ways. This is another way that we can say all real numbers. One final note about graphing. Sometimes graphs like to include parentheses and brackets, and other times we like to use the open dot and the closed dot to represent them. We use an open dot if it is like a parenthesis. So if it's a less than or a greater than, but it doesn't equal it, we'll use an open dot. we'll use a closed dot if it has the equal sign underneath it. This will hold true for some of the My Math Lab assignments, as well as some of the labs you'll go through. So I will show you both at times as we do our answers. Let's go ahead and graph each of these values, as well as write the answers in interval notation. First, we want to do x is less than or equal to -3. So I'll start with the number line, and I have 0, and I know -3 is to the left of it because it's smaller than 0. It says x is less than or equal to, so I will put a bracket here. I want all the values that are smaller than -3, and the only way we go smaller is if we go to the left. So I will shade all the values here going to the left. In interval notation, the way it works, we always took the smallest number on the left and the biggest number on the right. Here, -3 is the biggest value we can have in our answer because everything else to the right is unshaded. So I will put -3 to the right of our interval notation, and because it's got an equal sign, I will put a bracket. We notice it'll go forever to the left, and forever to the left is -infinity because it's getting smaller forever. Infinities always have parenthesis signs with it. So here is my interval notation. It's parentheses, -infinity, comma, -3 with a bracket. For my second one, I have x is greater than 2. Again, I'll put 0 here, and I know 2 is on the other side of 0 to the right, because 2 is bigger than 0. This time, it does not equal 2, so I'm going to put a parenthesis. I want all the values that are bigger than 2, which means I have to go forever to the right. So I will shade my graph to the right. Now here, 2 is the smallest possible value that we can have. Everything else is unshaded. So when I go to write an interval notation, 2 will go on the left side. But because it cannot equal 2, it gets a parenthesis. Again, it goes forever to the right, so that's my infinity. And infinities always get a parenthesis. Now just to make sure we understand the circles and the dots and the difference, if I were to regraph this one up here with a circle, I would go to -3, and because it's equal to it, I would do a closed dot at -3 and shade to the right. Here, if I was doing this graph from B, because it does not equal 2, I would do an open dot at 2 and shade to the right. The open dot and the closed dot are the same exact thing as parentheses and brackets. A couple more with interval notation. Now, you'll notice for this problem, the x is on the right side. Typically, we want to work with x on the left side because it goes through and reads the inequality better. So if you ever get in a situation where the x is on the right side, we can do an easy flip. Where basically, we're going to take the x and put it back on the left side. We'll take whatever value is on the left side, and it's going to go on the right side. And all we're going to do is flip our inequality to basically the opposite. So the opposite of being less than is being greater than. So 0 is less than x is the exact same thing as graphing x is greater than 0. So I'm at 0. It cannot equal 0. It's just greater than 0. So we're going to have a parenthesis. And it doesn't ever stop. So we're going to shade all the way to the right because all the values where x is greater than 0 are to the right. In interval notation, 0 is the smallest number. So it goes to the left side and it gets a parenthesis because it cannot equal 0. And it's going to go all the way to infinity, which always gets a parenthesis. Our last one here, we notice now it doesn't go forever. We have two numbers that are on each side. When we see this, we basically read this as x is between. So in this case, it's telling us x is between 0.5 and 3. It cannot equal 0.5 because it doesn't have an equal sign on this inequality, but it can equal 3. So when I go through and graph, I need to graph both numbers. I know 0.5 is to the right of 0, and I know 3 is to the right of that. It cannot equal 0.5, so we're going to have a parenthesis at 0.5, but it can equal 3. So we will put a bracket at 3. And it is saying x is between it. So we're going to go through and shade all the values between these. Because we have two numbers, there won't be any infinities this time. 0.5 is the smallest it can be, and 3 is the biggest. It can't include 0.5, so it gets a parenthesis, but it can include 3. So in his case, it gets a bracket. So when you have two numbers and an x is between those values, that is when you're not going to have any infinities. We will see more problems like this as we get to topic number 5. Let's go through and solve some inequalities. We'll graph it, and then we'll write the answer in interval notation. We're going to do this very similar to how we did linear equations back in topic number 1. The only difference is we always solve for the variable on the left side. This is different than how we did it in equations. In equations, we didn't care which side we solved it on. But in inequalities, it makes it easier if we solve the variable on the left side. So in order to do this here, we're going to have to move the 2x to the other side. This is a positive 2x, so I need to subtract 2x from the other side. Here they cancel. Negative 3x minus 2x is negative 5x. We'll drop down the positive 4, and then we'll drop down the negative 6. Again, very similar to how we solved equations. Our goal is to get x by itself. I have the negative 5x here. I need to move the 4 to the other side, so I'm going to subtract the 4. And whatever I do to one side, I'm going to do to the other. Negative 5x is greater than or equal to negative 10. In order to get x by itself, I'm going to need to divide by negative 5. But now here comes another very important rule, and probably the only other difference we really have when we talk about inequalities. And it's the rule that if we go through and we multiply or divide by a negative number, then we must flip the inequality sign. Basically what that means is we're going to take the inequality sign for what we have. So for example, if we had less than, it's going to flip to greater than. Or if we have less than or equal to, it will go through and flip to greater than or equal to. Going back to our problem, the negative 5's cancel. I have x here. Negative 10 divided by negative 5 is 2. But now the greater than or equal to now becomes less than or equal to. And so my final answer is x is less than or equal to 2. As a graph, we have 2 over here to the right of 0. It can equal 2, so we're going to have a parenthesis at 2. And we're going to shade all the values to the left. And it doesn't stop because it's not in between anything. In interval notation, 2 is the biggest possible number, so that is to the right of the interval notation. And it goes forever to the left, so we'll use negative infinity on the left side. And negative infinity and positive infinity always get a parenthesis. Here we have a problem similar to what we did in equations where we have fractions. We're going to use the same idea of going through and trying to find the least common denominator to go through and cancel out the fractions. Here we have 2, 3, and 6. My job is to find a number that all 3 of these numbers can go into. In this case, the common denominator happens to be 6. 6 can go into 6 evenly, 3 can go into 6 evenly, and 2 can go into 6 evenly. Knowing that, we're going to take each of these fractions and we're going to multiply it by 6. So here we've got 6 times 1, which is 6, divided by 2, plus 6 times 2, which is 12, divided by 3, is greater than or equal to 6 times x, which is just 6x, divided by 6. We can simplify these. 6 divided by 2 gives me 3, and 12 divided by 3 gives me 4, and 6 divided by 6x gives me x. Combining like terms, I have 7 is greater than or equal to x, but again, we like to go through and have x on the left side. So everything is going to switch. We're going to put the x to the left, we'll put the 7 to the right, but we're also going to go through and switch the inequality sign. So the greater than or equal to is now going to become a less than or equal to. So I have x is less than or equal to 7. 7 is to the right of 0. It can equal it, so we'll put a bracket. We want all the values that are less than it, so we're going to go through and shade it all the way to the left. In interval notation, 7 is the biggest number, and we can include it, so it gets a bracket. It's going to negative infinity, because it's going to the left forever, and infinities always get a parenthesis. Here we have a little bit more of a complicated problem. Again, we're going to do like we did with equations. We're going to clear the parentheses, combine any like terms, and then try to get x on the left side. So we're going to start by distributing the positive 7 here. And on this side, we're going to distribute the negative 4 here. 7 times x is 7x. 7 times negative 2 is negative 14. The x comes down with it, is greater than. Negative 4 times 5 is negative 20. Negative 4 times negative x is positive 4x. The negative 12 comes down with it. On the left side, we can combine 7x and x. They are like terms, so we'll go ahead and combine those. 7x plus x is 8x. The negative 14 will drop down with it. On the right side, we can combine negative 20 and negative 12. The 4x has nothing to combine with. So we'll drop the 4x down. Negative 20 minus 12 gives me negative 32. Again, our goal is to get x on the left side always. So in this case, we're going to move the positive 4x to the other side by subtracting it. And we're going to make sure we subtract it from its like term. 8x minus 4x is 4x. Drop down the negative 14, and it's greater than negative 32. We're going to get 4x by itself by adding the 14 to the other side. 4x is greater than negative 18, and our job is to divide by 4. Now notice, in this problem, only the negative on the top, not the bottom, so no flipping the signs here. We get x is greater than negative 18 over 4. Negative 18 over 4 can reduce because we can divide both numbers by 2. So really our answer is x is greater than negative 9 over 2. As I go through and graph it, I know negative 9 over 2 is a negative number, so it's to the left of 0. It's got the greater than sign, so I'm going to go through and use a parenthesis here, because it cannot equal negative 9 over 2. And then I want all the numbers greater than it. So I'm going to shade it to the right. Interval notation wise, negative 9 over 2 is the smallest the number can be, and we can't equal to it, so it gets parenthesis. Infinity is the biggest it can be, because it goes forever to the right. It also gets a parenthesis. Let's work the problem again with this one. Here I'm going to distribute the negative, and here I'm going to distribute the 3. Remember, there's no number in front. We pretend like it is a negative 1. Negative 1 times x is negative 1x. Negative 1 times negative 3 is positive 3. Plus 2 is less than or equal to 3 times 2x is 6x. 3 times negative 5 is negative 15. Plus x. Again, let's look for like terms. On the left side, 3 and 2 are like terms. And on the right side, the 6x and the x are like terms. Bringing everything down that we can. Negative 1x doesn't combine. 3 and 2 make 5. 6x plus x gives me 7x. And we'll drop down to negative 15. Again, if this were an equation, I would want to move the negative 1x to the right side. But with inequalities, we always want to go through and have the x on the left side. So I'm going to move the 7x in this case. We always want the x on the left side. We'll drop down to 5. And then we'll drop down to negative 15. Since the negative 8x is on the left, I'll get rid of the 5 by subtracting it. Negative 8x is less than or equal to negative 20. I want to get x by itself, so I'm going to divide by negative 8. But anytime I divide by negative, I have to flip the inequality sign. So I have x, instead of less than or equal to, I now have greater than or equal to. Here we have two negatives. Two negatives make it positive. So x is greater than 20 over 8. 4 can go into each of these numbers. So really we have x is greater than or equal to 5 over 2 as our answer. Graphically, 5 over 2 is a positive number, so it's to the right of 0. It can equal 5 over 2, so we're going to use a bracket. And it goes forever to the right, so we're going to shade it that way. Interval notation wise, 5 over 2 is on the left side, it's the smallest it can be, and it gets the bracket. And on the right, we get infinity with a parentheses. So again, a reminder, we always want to solve for x on the left side. It just makes it easier to graph as we go through. Let's show you a couple other ones. Here on this problem, we have some like terms. So I'm going to combine it, and we've got 2x plus x, which means I've got 3x. Now here again, my job is to get x on the left side. But in doing that, I notice that the x's are exactly the same. So they're going to cancel out. And in this case, I get negative 1 is less than 4. And so now I have to ask myself, is this a true statement? Is negative 1 less than 4? And in this case, the answer is yes. Negative 1 is less than 4. So if that happens, if you cancel out the variables and you get a true statement, then that means any value for x will make this true, which means your answer is all real numbers. How do we represent all real numbers? This is the one that graphically has everything shaded. So we would shade the entire graph, and every answer would work. So we would say our answer goes from negative infinity to positive infinity. This is very similar to in equations when we cancel out the variables, how we got our all solutions or no solutions. This time we're looking at the inequality and asking if it's a true or false statement. In this case, because negative 1 is less than 4, it is true, so we would get all real numbers. I think you can see what's going to happen here, but let's show you the other way. In this problem, we have x's on both sides. So I try to move the x to the left, and they end up canceling. And here I get 5 is greater than 7. And again, I ask myself, is this true? Is there a time when 5 is greater than 7? And the answer is no. 5 is always less than 7. So if I get no, that means I have no solution. There's no value of x that will make this work. Typically, we represent no solution with a 0 with a line through it. Graphically, it's just an open graph. We don't graph anything. And then in interval notation, we don't really have anything for that. We'll just go through and write the 0 with a line through it. So for the no solution and infinite solution, again, you'll cancel the variables, and you'll need to see, does the inequality that gives it to me a true or a false statement? If it's true and it works, then you'll go through and have all solutions. If it's false and it doesn't work, then you'll have no solutions. The last step, we're going to take you through a word problem with inequalities. And before we do that, here are some important keywords to help you solve inequalities. These are keywords that you can go through and recognize what inequality it's talking about. So for example, for greater than, it's above or is larger than. Whereas greater than or equal to is at least or is not less than. Less than, we could just use less than or fewer than or smaller. But less than or equal to, we'll use such things as is at most or is no more than. So these are great keywords to look for as we're going through and solving inequalities that are word problems. Let's try it here. A part-time salesperson earns $600 per month plus a commission of 20% of sales. Find the minimum amount of sales needed to receive a total income of at least $1,500 per month. So the unknown here is sales. We need to figure out how many sales to make our money. So in this case, we're going to call sales X. We need to make at least $1,500. So in this case, at least means we need to make greater than, or if not anything else, at least equal to $1,500. The salesperson earns $600 per month plus a 20% commission. So $600 per month plus 20% of her sales. We just don't know what the sales are yet, so we're going to call that X. And we need to find the minimum amount she needs to sell in order to make at least, so greater than or equal to, $1,500. So here is our inequality, and now we can go through and solve it. My job is to get X by itself, so I have to get rid of the positive 600. So I'm going to subtract the 600 from the other side. In this case, I get 0.20x is greater than or equal to 900. And to get X by itself, I'll divide by 0.20. When I do that, I get X is greater than or equal to 4,500, meaning she needs to sell $4,500 worth of her sales in order to earn at least $1,500 for the month. So again, using those keywords, I was able to figure out that at least is greater than or equal to. Use those keywords as you're translating word problems into inequalities.